Hi, everybody. Can I ask you guys to stop talking, please? Thank you. So today we're going to spend some time talking about this homework 7 that you guys, or that we talked about a little bit on the work from home day, but judging on what I saw in the homework check is probably something we should spend a little bit of time with, just to kind of refresh, the finer points of this. Okay. So will somebody grab the light for us? I'm assuming that the people in the back are probably going to have trouble seeing what's going on. Thank you. You're welcome. Okay. So the idea here for a linear program is that we're going to identify the solution space. That's the area on the XY axis of where all the potential solutions could live. It's basically the same idea as the homework 3.2, where we graphed the inequalities and found the area that was overlapping all the shaded regions. The same idea here. So to do that, we'll just kind of start graphing that. So I'll make a little XY axis for myself here.
Mr. Bullock?
Yes.
I can't see your screen.
Okay, let's fix that. Thank you. That should be better, right?
Yeah.
Okay.
Thank you.
You're welcome. Okay. You don't want to pop up there. I want you on the page. Okay. And that's a bit large. All right. So I'm going to start here just by graphing those 3 pieces, because to draw those parts of this is going to be really pretty straightforward. So y greater than 0 is like everything above the x-axis. So there's my y equals 0, and we're looking at the stuff above that. X is greater than 0, or really the line x equals 0 is the y-axis. So x greater than 0 is everything to the right of the y-axis. So really now the overlapping region is like the first quadrant. Is everybody okay with that? And then we have x is less than or equal to 8. So the line x equals 8 is just this vertical line that goes through the x coordinate of 8. And so with just those 3, what we've done is we're basically talking about this well as our solution space so far, right? Is everybody okay with that idea? Okay. So now let's worry about these other 2 inequalities. So the first thing I'm going to do is I'm going to rearrange so that I can get the y by itself. So the first inequality will add x to both sides. And then divide both sides by 2. So if I go to draw this line, I'd say have 0 and 1.5, and then like pick maybe 8, which will give me 5.5. Everybody okay there? Yeah.
Just to be sure, what we're doing is we can just use a slope intercept formula and then do the line that way.
Sure.
Okay.
Yeah. I just figured, I know that my solution set, the x values start with 0 and end with 8, so I figured I'll just have a point at each one of those and then connect them. But yeah, any points are going to be fine. So 0 and 1.5 is maybe there, and then 8 and 5.5 is maybe about there. So now our solution space is this like trapezoid, right? Is everybody okay with that? And then we have one more inequality to deal with. So I'll subtract x from both sides and then divide by -2. Remember though, when we do that, our inequality symbol is going to flip directions. So we have that. And again, I'll find some x's and y's on there. Doesn't matter which x's and y or which x's I choose to use. I'm going to use 0 and 8 because again, that's like the beginning and end of my possible x values that might be feasible. So when I plug in 0, I get -7/2 or -3.5. And I plug in 8, I get +0.5. So 0, -3.5 is maybe there-ish. And then 8 and 0.5 is maybe there. So what we've done is we just kind of cut off that little corner of our solution space. So that part is no longer included. We didn't lose a whole lot, but we lost a little. Is everybody okay there? Now that we've built this solution space, or I think I called it a convex hull, was another name you can call this, what we need to do is look at the possible solutions. So in my video, I said that the possible solutions are only going to be the vertices of our solution space here. So we have 1, 2, 3, 4, 5 points that we care about. Everybody okay with that? These are the only 5 points that we need to check now. We went from infinitely many in that pentagon there down to 5 that are just the vertices of that pentagon. So now all I'm going to do is figure out the coordinates for each of these 5 points. Now a lot of them I don't have to do much work to get. So for example, this point is just obviously the 0 is 0, 0, right? I'm going to refer to that as point A. This point here I'll call B. That's 0 and 1.5. This point over here, we'll call it C. And that's the point 8, 5.5. This point we'll call D, and that's the point 8, 0.5. And then the last one here is this point E. Now I know that the y-coordinate here is 0 because it's on the y-axis, but what I don't know is the x-coordinate for sure. That's the only one that I hadn't already calculated the point for or wasn't like totally obvious. Is everybody okay with how I got the coordinates for the rest of those? They're just things that we'd already plotted, right? Aside from 0, 0, which was hopefully pretty clear. Okay, so to figure out this x-coordinate here, all I'm going to do is I'm going to plug in 0 into the y value for the equation corresponding to that green line. Everybody's okay with that? And hopefully, without a whole lot of trouble, you can see that x clearly just has to be 7 there, right? 7 times 1/2 minus 7/2 has got to be 0. You could solve it algebraically if you wanted to, but I think that's one that you should be able to look at and just be like, oh, x is 7. You know what I mean? But whatever. Okay. So now we have our 5 vertices. So what I'm going to do now is I'm going to take those and plug them into the cost function and see which one gives us, since it's a maximization problem, the biggest cost. Okay with that plan? So for A, that's the 0.00, the cost is 0. For B, 0, 1.5, the cost is 0 times 3 is 3, and 2 times 1, or 0 times 3 is 0, and 2 times 1.5 is 3, so the cost is 3. C is 8, 5.5. 8 times 3 is 24. 2 times 5.5 is 11. 32 plus 11 is 43. So I have here the cost is 40. Oh, I'm sorry. 3 times 8 is 24. 11 times or plus 24 is 35. Is everybody still okay with what I'm doing here? Maddie? Mackenzie? This maximization equation, 3x plus 2y. You're welcome. Next up is D. So 8 times 3 is 24, and 2 times 1/2 is 1. 24 plus 1 is 25. And then E is 7, 0. 3 times 7 is 21, plus 0 is still 21. And since we're looking for the max, there's our solution. So the one with the biggest cost is point C. Is that okay with you guys? And I think that's like that's a problem that you could be able to handle on a test setting, right? We didn't have a whole lot to do on that. We just had to kind of understand the process, but there was nothing super tricky about that. It wasn't tremendously time consuming or long. It was pretty easy to generate a decent graph with the information that was provided. I think that that's pretty realistic to handle in a test setting. 2 is much, I think, is more involved than I would think would be realistic for you to do in a time test setting. We'll do it together, or at least kind of set it up together. We might not finish it, depending on what you guys feel like doing. But there's a lot going on there, right? So if we look at 2, we have, what do we have? 7 inequalities there, and none of them are easy ones to generate a graph for. Oops. So the first thing I would be doing is I would rewrite these so that they're in slope-intercept form. In the interest of time, let's just do that really quick. everybody okay with what we've written down there? So I just rearranged some stuff. And I would graph these. In the interest of time, I'm going to use the computer to do my graphing for me. Oops. I guess I don't want to do that. I need to be able to see these. So there's my first equation. So right now my solution space is everywhere below that line. There's my second equation. So right now, after these two are put together, my solution space is like everywhere down here, like the bottom of that X. The next one is this green line. So now my solution space is like below this red line to here, then below the green line, and then still below the blue line. Everybody's okay with that? Okay. Okay. And now we're below the yellow line. So now we've cut off the blue line entirely, right? The blue line no longer matters. Can we see that? So our region here is just basically between this little piece of the red line, the green line, and the yellow line. It's everything kind of down in here. Everybody's okay there? The next one, so now we're above the blue line, so we're in between the blue, yellow, and green, and we'll extend that out here so that we can see a little bit further. And I guess we got to go down a little bit too. So we're basically in this, well, it's almost a triangle. It's more like a quadrilateral, but because there's this little tiny side right there still from the red line. But we're basically in that quadrilateral, but bounded between the blue, the green, the yellow, and that little tiny piece of red still right there. And then our next one is x minus 2y equals 5. So there's that one. And we're below that one now, right? So now we've cut off the red line. It's now completely irrelevant. Oh no, we're above the orange line, right? That was a greater than because the sign flipped when we divide by the negative, right? So that gets rid of the blue line here, doesn't matter. So now we're between the orange, the green, the yellow, and that little tiny piece of red up there. Is everybody still okay? All right. So I'm going to readjust my window so that because I don't need any of this stuff over here anymore. So I'm going to do that real quick. We'll make that to negative 15 and that back down to negative 10. Okay, so we're just talking about this little space in here right now. And then our last one, 6x plus y equals 3. Then we're everything above this one, this light blue line. So that's just going to be this little tiny sliver of a triangle right in here. Everybody okay with that? All right. So again, I'm going to readjust my window a little bit so I can get a better look at what's going on there. It looks like if I go from negative 2 to positive 4 on the y, And then from like -1 to +2 or so on the x, that'll probably be good. And then we said -3 to +5 maybe, that should be good. So we're looking at this triangle right in here. So let me copy that. Uh-oh. AU. And I'm going to copy this. If I gave you anything this complicated, I would give you the picture already, just so you know. And our region that we're concerned about is this thing right here. Well, that's a bummer. So it looks like to me we have 1, 2, 3 places that we need to find the coordinates for the check. Do you guys agree with that? So this first spot up here seems quite obvious that that's 0, 3. I can read that off my graph. If I generated points, I would have found that point probably along the way. To find these other 2 points, though, I'm going to have to solve a system. So let's go ahead and let me go back to my equation and figure out what each one of them were. So for this point, my system is and it's like blue line 6x. Okay with that? So we'll solve these 2 systems. In the interest of time, I'm just going to estimate these since they don't come out to be necessarily nice, neat whole numbers. Everybody's okay with that plan? You could certainly solve these by hand, but I'm just going to create an estimate of those points just to kind of move forward on this problem, since we did the other one in fairly good detail. And we know how to solve a 2-variable system. I'm just have other parts that I want to talk about today that I want to make sure we leave some time for. Okay? So I'm just kind of streamlining this process a little bit. Okay? If you are unsure about the details that I'm leaving out, feel free to ask and I'll elaborate a little bit more, but I think we should be okay, right? And keep in mind that both of these are estimates. They're not going to be necessarily exactly those values. It's just going to be a reasonable estimate. You could solve them and find the exact values there, but again, in the interest of time, I'm going to scoot around doing that and just do these estimates. So we'll call this point B and this point C. So for A, 0, 3, I'll plug that back into the cost function here. So that's going to give me 2 times 0 minus 5 times 3, so negative 15. B is 0.7, comma 3.5. So that's going to be 1.4 minus 17.5, so that's going to be negative 15.6, is that right? No. 1.4 minus 17.5 should be negative 16.1. So I had too many numbers floating around in my head there. And then the last one, we have 0.8 comma negative 1.8. So the cost there, what do we have? We have 1.6 minus a negative 9. So that's going to be 10.6. So our winner then, since it's a minimization problem, is point B. Do you guys feel okay on that? Again, if I gave you something that was that odd, I would have given you the picture with the region shaded and identified what equations made up each of these lines involved, and then you would have just had to solve the systems and find the cost associated with each of the points. I wouldn't make you graph whatever 7 lines and try to find the shaded region. That's too much, right? One, it's hard to be that accurate when we're graphing, and 2, that's just a lot of stuff to keep track of in a time test setting. On a homework assignment, it's fine. You can take some time and use some technology if you need to, right? Like having the computer draw my lines for me made it much, much easier, and all I had to do was kind of keep track of where the shading was. Amy? So there's a kind of is the answer to that, at least as far as the graphing goes, which I think is probably what you're asking about. So, for example, if I wanted to graph y is, let's say, greater than 3x plus 6. So if it's a greater than, I'd be shading above, right? So what I'm going to do is I'm going to move my cursor over so it's on that little line before the y. And I'm going to press enter and cycle through the options here. So that option is the thick line. We don't want that. That option is the shading above. See how the top half of it looks like it's shaded? So that's the shade above. So let's use that one. If I hit graph now, when it draws that line, it's going to draw it with the shading above. Okay with that, Amy? The catch with this, though, is that if you have a bunch of these with shadings going on, it's going to do all of the shading and not just shade the overlap like you probably want it to. So like on a problem like the previous one where you have 7 lines going on, if you graphed them all as inequalities, it would look, I don't think I'd be able to tell the difference. You have the newer the color version, though, and it might be possible there to kind of keep track of what's going on, but that's the best your calculator can do as far as the inequality goes. Is that okay? Do we feel okay on these first 2 problems on kind of what to do or how to do them? Again, if you've don't feel great, go back and redo them. Like we have the video here. You've seen how to do them now in person. You know, you have the correct answer, so you can always go back and check things. Sergio?
Sorry, I didn't do that.
Just go ahead. No problem. Okay. The other two kinds of problems that we had, or the other kind of problem that we had to talk about here, were these kind of story problem situations. On these ones, all we're going to do is set up the linear program. I would not ask you to solve these ones. In most of the cases, there's far too many variables for that to be realistic. And realistically, like, if there's more than 2 variables, I really couldn't ask you to do anything with it. Even at 3 variables, where you can solve for the systems, the problem is you don't know if, like, the intersection you found is actually a vertex, or if it's like, you know, there's some other, it's like really cut off by some other piece. Like if we looked at the other problem, if we found all of the intersections, that's not really that helpful to us because not all the intersections of the lines mattered. You know what I mean? So like we just had to, so even if I gave you a 3 variable problem like this, it's still not really feasible for me to ask you to solve it because you need a picture to figure out which intersections you actually care about. So that's, yeah. So these are setup only kind of problems. We're not going to solve them in a course like this. Okay. All right. So the first problem reads, a car company needs to determine how many hours per day they utilize 3 robots they have available. Each robot has different energy requirements, operating costs, and capabilities that are noted below. The company needs to install at least 100,000 rivets a day and finish at least 12,800 feet of welding. The total energy consumed by the robots each day cannot exceed 500 kilowatt hours. Each robot can be used up to, I missed the number 20 there, 20 hours a day because of maintenance requirements. Formulate a linear program that models, or a linear programming model that minimizes the daily operating costs while complying with the production requirements. So the first thing we'd want to do is to identify the variables in this problem. So what are the quantities that we would need to solve for in order to answer this question? Maya. Very good. So I'm going to call those variables R1, R2, and R3. Okay, so those are our variables. Is everybody okay with that reasoning? And if you read the first sentence again, it would have been obvious since that's specifically what it's asking for, right? Is it wants those quantities. Okay. So the next thing, let's write our cost function. Is this cost function going to be a minimize or a maximize function? Minimize. How did you know that? Yeah, it says it right there, right? It minimizes, or it wants to determine the, yeah, minimize, right? Okay. So what quantity is it asking to minimize? The cost. So how would I calculate the cost of operating these machines? Amy? Good. And where she got those numbers was from the table, looking at the cost of operation per hour for each of the 3 robots. Everybody's okay with that? Okay. And then we have our constraints. So if we read the story, it says there's a bunch of requirements, like a bunch of work that these robots need to accomplish each day, right? Or a bunch of other things that the robots are required to do or not do, right? So what's another constraint that we could say here? Amy? Good. Oops. And the way she got the coefficients was, again, went to the table and found the energy requirement per hour of operation for each of the 3 robots. We so far so good? Okay. There are some other requirements, though, from the table. What's another requirement here on the table? Or in the story problem? Yeah, so, okay, we need 1,000,000 rivets. So how are we going to stipulate that? Oh, it's not there, right? It's not there today. What is your name? Regina Roos. Okay. And again, she got the coefficients by, again, looking at the number of rivets per hour of operation for robots 1, 2, and 3, respectively. Okay. I think there's a couple more here that I would still say that we can get pretty obviously. Amy, you have another? Mm-hmm. Good. Okay. And then we got a couple more still that I can see in here. Tom. Good. Very good. So how would we write that? Good. Good. Yep. And the R2 and R3 also, right? Okay. I would say that there's one other subtle requirement here that I think needs to be included. And it has to do not with anything necessarily in the story, but just with reality. Maya? Right, so that we have to make sure that the values for R1, R2, R3 really can't be negative numbers, right? Particularly when you're doing a minimization problem, you have to be cautious of that. Since R1, R2, R3 is the amount of time we're using a robot, the minimum value that time can have is 0, which means that, like, one way we could control it is here with the hours of operation requirement, or we could just do it here and state that these values have to be positive, which in turn makes the hours of operation also be positive. That's fine. Either one is okay to deal with. Is everybody okay there? And then you're done, right? We've got that thing completely set up. We've gone and looked at all the requirements. We have a cost function. We have variables that are clearly defined. So I would say that we're finished at that point. Amy? No, it's not supposed to be less than 30. It's supposed to be 10. Yeah, no, I wrote down the wrong number. You should double check those things, if only to point out to me that I wrote down the wrong number. Oh, good. Does that feel okay there? Okay. Good. Again, hopefully that was challenging, but probably realistic still feeling, right? After we've gone through and done it together, it's like, okay, I could do that again if I needed to, even if you weren't able to do it by yourself the first time. I don't think is too unrealistic. The next one is a little more challenging, but not, I think, tremendously more so. The next one says we need to determine a feed mix for a catfish farm. The total weight of the mix needs to be exactly 100 kilograms. The total protein in the mix should be at least 30 kilograms. The total digestible energy should be at least 250 ml. The amount of calcium should be at least 0.5 kilogram and at most 8 kilogram. Furthermore, the amount of fish meal should be at least 8 kilogram and the amount of rice bran should be no more than 20 kilogram. The costs, protein content, digestible energy, and calcium content for the possible ingredients in the mix are included in the table below. Note the protein and calcium contents in the table are in percentages of the requirement of protein and calcium contents in the mix are in kilograms. Formulate a linear programming model that can be used to satisfy the catfish feed requirements at the minimum cost. Okay, so let's start with identifying the variables. So what are the variables in this problem here? Okay, the ingredients, I would say we should be a little bit more specific than that, though. Regina? Yeah, the mass of each ingredient in kilograms. Yep. So I would use I'm just going to use the letters M, F, S, R, and L for maize, fish meal, soy meal, rice bran, and limestone to represent the quantity of each of those ingredients. Everybody okay with that? So let's write our cost function now. Should this be a minimization or a maximization problem? Minimization problem, good. And again, we know that just because it tells us. So how would we calculate then the cost of our feed mix? Amy? Good. And she got those numbers just by looking at the cost column from our table. You guys okay with that? So here is an important point as to why these ingredients represented in kilograms make a big difference here, right? Because if not, we didn't need another conversion factor before we applied that coefficient. So that's good. Okay, now let's start worrying about our constraints. Can anybody tell me one possible constraint? We have several that we could write from the table. Jack?
All of them actually
Good. So M plus F plus S plus R plus L has to equal 100. Very good. Did anybody catch why that requirement is going to be so important? So keep in mind, in our table, we have some things that are listed as a percentage and some things that are listed as kilograms, right? Why would having the total mass of our mix equal 100 be really useful to us? Right. Basically, if that's the case, then 1% of the mixture is 1 kilogram in mass, right? Is that kilograms and percentages just can be used interchangeably. If the total mass is 100, it makes that really nice. So that's quite helpful. And it makes the table conversion really non-existent, right? We can just use kilograms and percentages like they were the same thing. Cool. All right. What's next? What's another constraint? Oh. Tommy.
The amount of calcium to be at least 0.5 kilograms at most 3 kilograms.
Okay, so how would I write that?
0.5 is less than 0.02 m plus 2.7 s plus 0.3 s plus 0.1 r, which is 8 out, and less than 8.
Good. And again, where did he get those coefficients from? Just use the calcium list there, right? Okay. What's another constraint? Jack?
The fifth one has to be greater than or equal to.
Okay. And Maddie, you had your hand, or I'm sorry, Mackenzie, you had your hand up, right? Okay, so the first one for the protein should be at least 30 kilograms. How do we write that? So that's close. We're also going to need the percentage of protein for each of them factored in, right? Because each of their masses is not straight protein. So for example, I'd have 9m plus 65f plus 44 s plus 12r plus 0l has to be less than or equal to 30. And really, I guess these should be decimal points, right? Oops. Did we have to do the same thing back there? Let's do this. That'll be easier. Let's not put the decimal points here. Let's put them here. That'll be easier to deal with. Does everybody agree with that? Well, I don't think that's the case, because if f is at least 8, 8 times 65 is automatically going to be bigger than 30, right? So like there's no solution to that. I think that, because if we think about it, like 9% of 100 should be 9, right? So I just have like, if I had 100 kilograms of maize, I should only have 9 kilograms of protein in that. So I think that we have to do, if I multiply the masses by 9, we have to do some kind of, these percentages have to work out in some way here, right? So let me think. This, I don't divide both sides by 8 or by 100. So I would make, we multiply each side by 100. Would that be right then? Let's think about that for a minute. Oh, sure. Thank you. Good. Yes, so let's think about that for a moment now. Yeah, I think that this should be well, I guess that's probably right. I guess we probably don't have to do that, right? Yeah, if 1 kilogram is 1%, then that should be yes. Okay, I'm convinced. You're right. So we don't have to mess with any of that. Thank you. Okay. Next up, let's look at what we've done so far. Right? We took care of the total weight. That's been done. The total protein, the calcium. We did the fish. We have 2 more to do, right? So we still need to do the digestible energy and the rice bran. What would I write for the digestible energy? I'm just going to do the same thing. It's to be at least 250 meal. Okay, and then we're told the rice bran has to be at most 20 kilograms. Everybody okay with that? I would say there's one more set of hidden constraints here that we need to be careful about. Regina? Yeah, so certainly R has to be positive, and I would include then that also S, L, and M also have to be positive. I don't have to do that for F though. It's not wrong to list it for F, but we don't need to write it. Why can we skip it for F? Because we already know that it has to be greater than 8, and clearly that's bigger than 0 already. But again, in particular for these problems where we're doing a minimization, we got to make sure that we're stipulating if things can be negative or not. Because if they could, maybe it's like, oh, we'll just have negative 10,000 kilograms of limestone or something, and that'll make somehow make the cheapest mixture. Because limestone is, or maybe negative 10,000 kilograms of soy meal, because soy meal is pretty expensive, so that gives me a big cost savings. You know what I mean? Like, you can do something silly like that. Or we'll just have like a ton of calcium and a ton of limestone and very little, all this negative soy meal, and somehow end up with a really cheap, mix, because it's now negative to cost. Like it's a negative cost to manufacture it, which is nonsense, right? Like, oh, we're getting paid to do this. Anyways, everybody feel okay there? Okay. Again, hopefully this was a little bit trickier because of the whole percentage thing with the 100 kilograms. But once we pointed that out to you and we double checked and thought about it for a minute to make sure that we didn't have to do anything funny with the numbers in the table, everything was okay. This last one, I think, is the most challenging one, because of deciding what the variable needs to be is to make it as simple as possible is a little bit, I think it's kind of tricky. So it says a post office requires a different number of full-time employees on each different day of the week. The number of full-time employees required on each given day is given in the table below. Union rules state that each full-time employee must work 5 consecutive days, then receive 2 days off. For an example, an employee who works Monday through Friday must be off Saturday and Sunday. The post office wants to meet its daily requirements using only full-time employees. Formulate a linear programming model that the post office can use to minimize the number of full-time employees that must be hired. So again, we'll start by trying to determine what the variables are. So initial thoughts. Again, like, it's okay to be wrong about stuff. We'll talk this through. This one is, I think, rather tricky once, at least to get it started. Amy, you have a thought as to what the variables? Okay, so that's the natural first thought, right? So the problem is the workers on Monday are going to come from a bunch of different scheduled workers, right? So how do we tell the difference between the workers on Monday that are coming from one schedule versus another schedule? It's not entirely clear, right? Maya, you have an idea? Okay, that could be like one variable. What would another variable be? Okay, so basically you're talking about the number of workers that work each of possible schedule, right? That's the key there, yes. So we just have the variables are going to be the number of workers for each possible schedule. So let's write down the different types of schedules then, right? So Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So one possible schedule, we work Monday, Tuesday, Wednesday, Thursday, Friday, and we're off Saturday and Sunday, right? And then Maya said the next schedule would have been working Tuesday, Wednesday, Thursday, Friday, Saturday, and then we're off Sunday and Monday. What's another schedule? Start Wednesday and work through Sunday, so we're off Monday and Tuesday. So we'll start Thursday and we'll work through Monday. Okay, so we're off Tuesday and Wednesday. What's another one? So starting Friday, so work Friday, Saturday, Sunday, Monday, Tuesday, we're off Wednesday and Thursday. Is that the worst possible schedule? Feels like that would be not fun to work. Continue. Are there more? Start Saturday, so we work Saturday, Sunday, Monday, Tuesday, Wednesday. We're off Thursday and Friday. Start Sunday, and then we work through till Thursday, and we're off Friday and Saturday. Is there another? Jack? Yeah, so let's go back and read the problem and try to determine that. So it says the number of full-time employees required to work on each given day is given by the table. Union rules state that each full-time employee must work 5 consecutive days and then receive 2 days off. So yes, and that's important, right? If not, we'd have a lot more possible schedules. But with that requirement, we have just 7 possible schedules. Everybody agree with that? So the variables I'm going to name are just going to be S1, S2, S3, all the way out to S7. That's what I'm going to name them anyways. You could name them something else if you wanted, but good with that. Okay. So the cost function then, are we going to be minimizing or maximizing here? So I think it said to minimize the number of workers. And how would I calculate the number of workers? Amy? Not quite. It's a little bit simpler than that. Remember what these S variables are representing. So we said that the S's are representing the number of workers for each schedule. So the cost function, to figure out the total number of workers, what do we have to do, Maya? Yeah. That's all it's going to be. Yep. So if we just add up our 7 variables, that'll give us the total number of workers that we have employed, right? Because we have nobody that doesn't work a 5-day schedule. Is everybody good with that? Okay. And now what are the constraints here? What information haven't we used yet? Maya? Yeah, so there's this data in the table where we have the required number of employees for each day of the week. We haven't used that information yet to do anything, right? Not in how we've determined what our variables should be, not in the formulation of our cost function. So these are going to have to make up or be information used for the requirements. Everybody agree with that? Okay. So how are we going to calculate, for example, the number of workers we have for a Monday? This will be helpful. We look at this table that we built. Loretta, are you stretching or are you raising your hand? Okay, I'm just checking. I'm not going to call on you if you don't want to be called on. I'm just double checking. So which day of the week are we talking about right now? Monday, right? Okay. So what schedules do we have workers working on Monday? Loretta? Yes. And that has to be at least, what is it on 17? Is everybody okay with that? That'll tell us the total number of workers we have for Monday, because that'll involves all the workers that work the schedules that have to work on Monday. Right? Does that make sense? Okay. So let's do the same thing now for Tuesday. What would be the Tuesday constraint? What is the number? 13. Everybody okay there? Okay. How about the Wednesday constraint? Okay. And then the number was 15. Okay. And Thursday would be? Is that what I said? Thursday was 1, 2, 3, 4, and 7. Okay. And that has to be at least, is this the 19? Okay. And then for Friday, 3, 4, 5. How many do we need on Friday? 14. Okay. And then the next one is Saturday. Okay. I think there was 16 we need for Saturday. And the last one is Sunday, right? Thank you. Okay. Are there any other constraints here? Are there any other constraints that we have to worry about? What are these variables representing again? The number of workers that can work a schedule, right?
We need at least over 0, we need at least 1 worker.
Okay, so each of these workers, or each of the workers working a schedule, certainly they have to be greater than 0, right? Can't have negative workers for a day. True. And there's another constraint still that I feel like that we need to include. Jack? Well, that'll get handled. We'll handle that there. Mackenzie? Again, we handled that with the construction of our variable. So the fact that we define these S's as the number of workers per schedule, and we define the schedules as 5 days, consecutive days. We don't need to worry about that. Loretta? What does that mean? Okay. So full-time, so these are full-time workers, right? So what kind of values would be acceptable? Whole numbers, right? We can't have like 7.32 full-time workers for a schedule. So we should also say that these guys are integers, right? Have to be whole numbers. And combine that with greater than 0, we're talking, or greater than or equal to 0, we're talking about positive integers, or non-negative integers anyways. But that's going to be then the constraints for that one. That's harder than I would expect you guys to be able to do on a test. I think the previous two are realistic. I probably wouldn't have anything as involved as the second one. There's just a lot of constraints to sort through there. But I think the first one's pretty realistic for you to be able to handle in a test setting. Do you guys feel better about this assignment after kind of walking through it carefully, slowly here as a group?
I had no idea how to do this.
Yeah, it's okay. This one was quite difficult. It's not obvious at all that the variable should be the number of workers per schedule. Right? That's a big, difficult observation to have made. Right?
Yeah.
So the natural thing would have been focusing on the number of workers per day, which is hard to sort out. So I don't have anything for you guys to do for tomorrow. There's no homework for tonight. We just did this today. We still have a bit more to do this chapter before there's a test, so that's not coming anytime soon. Because there's like a second piece to this chapter where we're going to look at another way of kind of solving these systems. We need to build out a little bit of infrastructure in order to do that. So the second half of this chapter will be kind of devoted to building out that infrastructure and then tying it back into solving a system. So we'll take a little break from system solving for a minute to build out this new way of doing things. And then we'll tie that back together to solving systems here at the end. But that'll be, we'll have, I don't know, 3 or 4 class days of kind of doing that before we're tying everything back together again at the end. Okay? But I'm done for you guys today. Go to lunch or your next class or wherever you go next. Have a good day. You're welcome. Bye, Loretta. Bye, guys.
Bye, thank you.
You're welcome. Bye-bye. Bye.